We've already seen that composing permutations is a lot like multiplying non-zero real numbers, and we're going to push that analogy a bit further in this lecture when we define powers of permutations in precisely the same way that we define powers of real numbers. So that definition is written at the top here, and here it is. If we have a permutation s and an integer m, then s to the power m is defined in three different ways according to the value of m. So if m is strictly positive, then s to the power m means s composed with s composed with s composed with s m times. On the other hand, if m is 0, then s to the power 0 is defined to be the identity permutation. And finally, if m is strictly negative, then s to the power m is defined to be the inverse of s composed with the inverse of s composed with the inverse of s, and so on, minus m times. So if you think about it, this is precisely how we define s to the power m if s was a real number. Let's see some examples of this, starting with the permutation s, here being this permutation in two-row notation, whose disjoint cycle decomposition is just the 2-cycle 2, 3. So if we do this, then s squared means s composed with s. So this is 2, 3 composed with 2, 3. If we want to work this out, well, perhaps we can do it simply by writing down the two-row notation for this. So we'll think one number at a time, what s squared does to that number. S squared of 1 is s of 1. S of 1 is 1, so s of 1 is 1 as well, so 1 goes to 1. On the other hand, let's try to see what happens to 2. So s of 2 is 3, s of 3 is back to 2 again, so s squared of 2 is 2, and s squared of 3 must be 3, since we've got to have a 3 on that bottom row somewhere. So s squared is actually the identity permutation. And if we want to know s cubed, well, we could work this out carefully by thinking what is s of 1 and s of s of 2, but it's better to step back a bit and think about associativity of composition. So s cubed is s, which I can think of, if I like, as s composed with s. But we know s composed with s, that's s squared, and that's the identity. So this is s composed with the identity. And of course, composing with the identity does nothing. So this is just s again. So what will happen, in fact, if we take further powers of s, is that it will simply repeat itself. S to the 4 will be the identity, s to the 5 will be s, s to the 6 will be the identity, s to the 7 will be s, and so on. So let's look at a slightly more interesting example now, which is this permutation t, which in two-row form has bottom row 2, 3, 1, and which as a cycle is the 3-cycle 1, 2, 3. So if we work out t squared, well, this is 1, 2, 3 composed with 1, 2, 3. So let's try and write this as a cycle straight away. What happens to 1? Well, first of all, 1 goes to 2, and next 2 goes to 3. So 1 is sent to 3, and then 3 goes back to 1 here, and then goes to 2. So 3 goes to 2, and then finally 2 goes to 3 here, and then 3 goes back to 1. So we've completed our cycle, and t squared is equal to the 3-cycle 1, 3, 2. Let's now work out t cubed. So t cubed, I can think of this as t times t times t, and again this is t times t squared. And of course we've just worked out t squared here, it's 1, 3, 2. So what we've got here is 1, 2, 3 composed with 1, 3, 2. And actually you should do this composition, and if you do it, what you'll find is that you get the identity permutation. Let's do some negative powers. So t to the minus 1 means the inverse of t. we can get the inverse of t in the usual way. Well, we have two ways of doing this. So one is to take the two-row notation here for t and swap the two rows and then reorder the columns. Or the other way is to simply write the cycle notation for t in the opposite order. So let's just do that. I mean, writing the cycle in the opposite order, t inverse is 3, 2, 1. But now we've done this, we can work out t to the minus 2, because the meaning of t to the minus 2 is t to the minus 1 composed with itself 2 times. So this should be 3, 2, 1 composed with 3, 2, 1, which, again, if you work this out, what happens to 1? 1 goes to 3, 3 goes to 2. What happens to 2? 2 goes to 1, and then 1 goes to 3, and then 3 goes to 2, and 2 goes to 1, so the cycle finishes there, and t to the minus 2 is 1, 2, 3. So actually this is t again, if we look at it. And this was equal, again, if you think about it, t squared. So again, you've got this repeating pattern, so this time repeating forward and backwards. So if we take positive powers of t, we get t squared, and then t cubed is the identity, so t to the 4 will be t, and t to the 5 will be t squared, and t to the 6 will be the identity, and t to the 7 will be t, and so on. And we get the same kind of repeating pattern looking at negative powers as well. So t to the minus 1 is t squared, t to the minus 2 is t to the minus 3 will be the identity, t to the minus 4 will be t squared again, and so on. Another way in which powers of permutations are similar to powers of real numbers is that it's actually quite easy to prove, just using the definition which I've written of the power of a permutation, that the ordinary exponent laws for taking powers of real numbers are also true for powers of permutations. So in particular, looking at these two laws down here, if you multiply s to the a and s to the b, you get s to the a plus b for any permutation s and any integers a and b. And also, if you take a permutation s and you do s to the power a and then you raise that to the power b, that's the same as doing s to the power a times b. So these exponent laws are often useful if you're simplifying a complicated expression using permutations. Our next definition to do with permutations is the order of a permutation. And the order of a permutation s, which we write as little o of s, like this, is the smallest strictly positive number n, such that s to the power n is the identity. Let's see some examples of computing orders of permutations then. So beginning with this one here, s is the permutation, which is the 2-cycle 2, 3. And then, as we've seen before, s squared is equal to the identity. So s to the 1 is not the identity, s to the power 2 is the identity, so 2 is the smallest power of s equal to the identity. So the order of s is 2. And here's another example, t, which again we've done before. This time t is not equal to the identity. T squared, we worked this out and we saw that it was 3. Well, I wrote it before as 1, 3, 2, and that's not the identity. But t cubed is the identity. So the smallest strictly positive power of t equal to the identity is the third power, so order of t is equal to 3. And here's a couple of examples which you might like to check yourself. Here is u, which is the permutation which has a disjoint cycle decomposition of 3, 4 times 1, 2. And in fact, what you'll find is that u squared is equal to the identity, so the order of u is 2. On the other hand, if you take this permutation v, which is the 4-cycle 1, 2, 3, 4, if you check the first 4 powers of v, what you will find is that the order of v is 4. Now, we don't really want to have to work out each time all of the powers of a permutation to find out what its order is. So it's helpful to have the following result, which is a theorem about the order of an m cycle. And what the theorem says is that the order of an M cycle is M. So I'm not going to prove this because it's going to be something you will prove on an example sheet. And what I will do is make a few suggestions just about how to do this. And my first suggestion is that whenever you have a problem, a mathematical problem at least, which you're not quite sure how to solve, a good question to ask is always, can I solve an easier problem? And an easier problem in this context, where you're trying to prove that the order of an M cycle is M, is to think, well, what if the M cycle was, what if it was just 1, 2, 3, 4, 5? Or what if we chose a specific example of an M cycle which was just 1, 2, 3, 4, 5, 6, 7, up to whatever M was? So doing this makes the problem a little bit more concrete. You may find that when you've solved the problem in this specific case, that shows you how to answer the general case. That's why solving an easier problem is often a good step to solving a harder problem, because often when you solve the easier problem, it shows you how to do the harder problem. My second suggestion is one which we saw in our in one or two videos ago, and that was to think about notation, because often the hard thing when you're proving something is you may understand why the result is true, but it can be difficult to write it down in a way that another person would understand or find convincing. And often a good choice of notation can help it make it much easier to express your ideas in a proof. And the helpful idea here is to give your M cycle a name. So let's call it C, and let's notate that M cycle like this. And then to extend the notation. So we will define AM to be A0, and AM plus 1 to be A1, and AM plus 2 to be equal to A2. And the reason for doing that is, well, as we saw before, it was useful to have this property that we can now say a C of AI is equal to AI plus 1 for any I, not just I between 0 and m minus 1, but any I. But it's also helpful to have this because now we can think about what would C squared do. So C squared of AI, well, what would it be? You should think about that. And this is a helpful thing to do, because when you're trying to solve this problem, to prove that the order of an M cycle is M, what you're looking at is, there's the definition at the bottom of the screen, you're looking for the smallest power of C, which is equal to the identity permutation. So a good description of what powers of C do is going to be useful to you in finding out which is the smallest power, which is equal to the identity.